Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So let's continue with the gravity compensation methods. So what we have been talking about, so we can use counterweights to compensate for gravity, but at the same time we can also use springs. So for instance, in this case, what we have is a mass here, and it has to be suspended, and mechanism has to be designed to take care of the gravity. So whether we can place it in any location uh, without using any kind of force or actuation. So whether we can use a spring for that. So here you have a spring. So what you realize that, so in order to get zero force input, so the total energy here what we have is stored in the spring, and the weight mgh itself. So d by d phi of the total energy should be 0, and we should be able to get some relationship so that we can design such mechanisms. So if we look at this design, yes, the spring here, what we are referring here is this zero length spring. So what does it mean is delta itself is the length. So whatever is the change is the length itself. It has initial zero length. So we have discussed about some of the configuration, how to achieve this kind of zero length springs. So we can refer to that. So if we check here this configuration, so we have angle phi, and these parameters A and B. So that's where the spring is attached, A and B. So the length of the spring when it has position at that location is L, and which can be given by, and can be written with respect to the phi and with respect to A and B. So L square is equal to A square plus B square minus 2AB cos phi. I think we all know that. So if we consider triangle AM and B, so if we just go with that, the potential energy stored in this spring because of that deformation, elongation of the spring, it can be simply written as half CL square, because delta is the length itself. So if we do that, then we can write half CL square. So we can simply substitute that. So here we have 1 by 2 C, and under bracket you have A square plus B square minus 2AB cos phi. So this is the relationship for the potential energy stored in the spring. Similarly, so this was for the spring. Similarly, because of the gravity, so and we are shifting the weight, positioning it. So it can be some mass, it can be a speaker, it can be some kind of unit, cabinet we want to position with much without any effort. So yeah, because of the mass itself, the mgh, so mg, and the because of the repositioning, so h is maybe corresponding to m, so h0 plus r cos phi. So that is because of the gravity. So the total energy can be written in terms of the potential energy stored in the spring, and because of the weight, the gravitational force. So u spring plus u gravity, and what we want is the derivative with respect to the to phi should be 0. So if we are able to achieve this, then it's stable in every location. It's independent of phi. So if we write the du spring by d phi, so with respect to the orientation d phi, so we can simply substitute for the potential energy stored in the spring here. So half c, and the L square, which is a square plus b square minus 2ab cos phi. So what we see here is most of the parameters, this is constant. What is the parameter we have is cos phi, and if we just take everything out, this will be 0, the constant terms will be 0, and then minus and 2 will get cancelled. So if we take the derivative, it will be 1 by 2 minus 2ab, and cos will be minus sin phi, so minus minus plus, and sin phi, and 2 will get cancelled. So we are left with ab sin phi times c, cab. So yeah, we can put the subscript ab. So the stiffness of the spring times a times b sin phi. So this is what we get if you take the derivative. Similarly, for the gravity term, we take the derivative of the potential energy because of the gravity mgh. So h can be written in terms of h naught plus r cos phi. So this is the term which is variable, and if we write, what we find that the constant term will come out m, g, and r, and cos phi is minus sin phi, and this is what we are getting here. So the first derivative will give us this value minus mgr sin phi. So if you want to get the derivative of the total energy, so we can simply sum and equate it to 0. So for a spring, this is CAB AB sin phi. For gravity term is minus mgr sin phi, and that is equal to 0. So sin phi is the common term, to we can take it out. Of course, that cannot be 0. So the coefficient has to be 0, and if we just take it out, make it 0, what we realize that the stiffness of the spring CAB times A times B should be equal to mg times this R. So this is the CAB. So very interesting and very useful formula, very useful condition we are getting. And if we are able to satisfy this condition, C times A times B is equal to mg times the R, the link length where the weight is suspended. So we should be able to get a very good gravity compensator using the zero length spring. Of course, R is the from M to the CG of the body. So it should be the CG, and this is the weight. So I think this can be tried and can be used in many applications, and we can get a very useful mechanism. Similarly, in many of the systems and like for medical application, CT scans, the patient has to be inserted inside for the scan, and you can design the bed to position and lift the patient. So there can be various ways. So there are two designs. In one design, you are using just one actuator, and the weight is guided by a vertical column using these two rollers. In the other one, here you are using two actuators, and you try to manage both the lift and the also want to compensate the tilt. So what is the difference? So if we look at the first design, what we realize that we have only one actuator here, and the moment is completely managed by these two rollers, right? So weight is offset mg. So because of there is a moment, and the moment will be taken care by the guide. So we can have a central guide which will take care of any tilt. The actuator is only for the vertical lift. So if we do the balancing, what we realize that RB is nothing but simply mg here. There will be no RA because it's free to go up and down. So RA will be 0. RB will only provide the lift, which will be equal to mg. Any moment that will be taken care by the guide itself, this vertical guide which is moving up and down. So what we realize that if this is the force, so this will be experienced by the actuator and times V. So F times V will give us the power. So this is the power required by the actuator in this case. So only one actuator, and it's a passive. So centrally supported. So it will take care of any tilting, and moment will be balanced. But the actuator, only one actuator, only taking care of the vertical lift. In the other case, here you have two actuations, and one may think, yes, this may be a better design because you have two actuators and it can distribute. But if you look at the calculations and try to look at it, what we realize that because of the offset, this mg, the weight, A1 and A2 has to take care of the moment because of that offset, but at the same time it has to also take care of the lift. So we can do a quick calculation. So suppose this is point O and this is say M. So if we just try to balance the moment at O, and that has to be 0, what it gives is RB times B is equal to mg times A. So here RB will be so what we realize that so if we do that, what we realize that RB will be so RB can be written as mg times A by B. Similarly, if we try to do the moment balance at M, which has to be 0, then what we realize that RA times B is equal to mg A plus B. So this will give us RA equal to mg 1 plus A by B. So the two actuators, these are the two forces they will experience, and if they have to lift the patient with velocity v, so if the patient has to be lifted, so F times v, so what the power will be basically RA plus RB times v, and if we just substitute that, what we realize that we get mgv times A plus 2 times A by B. So if we compare the power requirement of the two actuators in two cases, the consumption, although the second case, if we don't do the calculation, we may fall for it and we say that there are two actuators, so maybe a better solution. But after doing the calculation, we realize that that's not true. So in the first case is simply mg times v, but in the second case is mg v times 1 plus 2 A by B. So this is the extra term we are getting. So I think one has to be very careful when we are designing systems, and we have to always check whether it's giving us any advantage. So we should be aware of that. And there are many methods. So any system we are designing, we have to look at the energy aspect, and if we can take care of those things, there's the size of the actuators, and sometimes we don't even need any kind of actuations, and we can just use passive methods. So it's a very good way, and knowing and understanding these methods will always help us to design better precision mechanisms for our different applications. So there are many examples. We can refer to the books. So whatever uh, I discuss here is just some cases, some examples, just to show how it can be done. So moving on, so we'll quickly talk about dynamics and any precision system. If we talk about, what we realize that the mechanical design or just designing it for failure or for stiffness and precision may not be sufficient. It has to be also controlled. Whatever is the error, whatever is the dynamics, so we'll learn that has to be compensated. In some cases, it can be compensated. In some cases, it might not be possible. So therefore, it's very important to understand how the system will behave under different kind of motions. If we give different kind of inputs, what will happen to the system? And knowing that, I think it will let us design better systems. Many of the things we learn in vibration courses. So for instance, if we take any mechanical system, most of the time we can design it as a second order system with a stiffness C and some damping here D and mass M. So these are the parameters many times we talk about. Yes, in the systems we can have a damping because of the joints and other means. If not, then we may have to introduce damping to the system, either electromechanically or by some other means. What we realize with respect to the flexures, since there is no sliding or rotating contact, there is no direct physical contact, the damping is many times quite less. So we may have to introduce additional damping if it's required. So, but in most of the cases, a second order system and slightly damped, we can model it like this. What we'd be interested in, if this is the input and this is the output motion, so h prime t, that's the, if the bottom, the reference is moving, how the output, this x dot and x double dot, so displacement, velocity and acceleration, how it moves and whether we can control it. So we'll try to look at the behavior, the response. So we can consider a very simple system where you are interested at the output here x, and the input is the cam motion here, so ht here, and we have a lever connected with the parameters a and b. So usually this is the kind of we can have a different kind of cam design and a different kind of motions can be given to the system. So this is one of the case. This is the displacement we are talking about, and this is the acceleration. So we can see that even though the displacement curve can be very smooth, but uh, in cam design and when we talk about kinematics, what we realize that the acceleration parameters can be very different, and it can have a very big amplitude and many times discontinuous, and that can give rise to a lot of issues. So we'll look at it when we compare and try to model it. So we can say that is a very low damped system. So B is the the damping is more or less 0. So, only spring mass system. So, we can model it like this, and the input is h prime t. So, h prime t is because of the motion of the cam, which is ht, and because of the lever here, b and a terms will come. So, we can check. So, it will get amplified. So, this is the input coming to the or received by the system at the output, and in between this is the stiffness of the lever here, and if that is the case, what is the output? X dot and x double dot. So, for different kind of cam motion. So, when we look at the mass spring systems, and if this is the displacement x and x dot x double dot direction. So, the stiffness is defined, and so if we make the free body diagram, and what we realize, if we write the dynamic equation, the governing equation, mx dot double dot is given by, because the spring, the x is defined in the vertical upward direction. So, it's a minus Cx, that is the force. So, that will be equal to minus Cx, and so this is the governing equation we can write, mx double dot plus Cx equal to 0. And the solution for this kind of differential equation, we know that is can be written. So, amplitude x cap times sine omega et plus phi, and from here also we know that x double dot is minus c by m x. So, or we can simply write in terms of a cos omega t and plus b cos omega t. So, these are the general solution for this kind of equation we know from many vibration courses in our undergrads. And we also talk about the resonance. So, the resonance frequency omega will be given by under root. So, this is omega square, and from here we can find this. So, mind that it's radian per second under root c by m. If it's in hertz, we have 1 by 2 pi included. So, this we should be aware of. For any kind of input motion given here h prime t, what is the response? And if you are looking at what it can be modeled as, simply as a force here, c h prime t. So, therefore, the dynamic equation can be, the governing equation will be mx dot double dot plus cx is equal to this force what we have, which is because of that input motion c times h prime t. So, we can use it and try to see the second order response for different kind of input. So, suppose if we give a position, a step input, what happens? So, if so just hm, that is the position input we have given to the system. So, as we said, it is equivalent to c times hm. So, this will be my governing differential equation. Damping is 0. So, if we write the solution for this. So this is the general equation, and this is the particular solution HM, because that's what we are providing. So if we just put this boundary condition, what we realize that A is minus HM and B is 0. So this term is 0. So we will be left with xt can be written as HM times 1 minus cos omega t. So what we observe that if there is no damping and only a spring mass system, so it will oscillate. So this is the amplitude for the displacement HM. For the velocity is omega times HM, and for acceleration this omega square HM. So that is the amplitude, and when we look at it, this is how the system will behave. So this will be the position, the displacement, and x dot and x double dot will be like that. And what we realize that the positioning error, dynamic positioning error, is plus minus HM, so which is evident from this plot. And the acceleration will be omega square HM, which is very high. So now think of a system having a very high stiffness. So for instance, a car with a car, or even SUVs, you can say these days. So if the suspension is hard, so and suddenly if there is a step, a stone, curved stone, a vehicle is moving very fast, and suddenly if suppose there is a step, what happens? And what we realize that this is way high. But if it's a softer, so some sedan and so very good suspension, you will feel very less vibration. But if it's some kind of SUV with very hard suspensions, you will have trouble. So from there also we can correlate. What happens if we have a velocity step? So in case of velocity step, the output is C Vv times t here. So this is the representative plot. If we give a velocity step, suddenly a velocity input is provided. So how the system will respond? So again is the velocity. So it's and what we can find that is the velocity x dot is Vv times 1 minus cos omega t, which is this. So the velocity is fluctuating, and these are the response, displacement, velocity, and the acceleration plots. But we realize that the positioning error is this much, and this is your acceleration amplitude, and this is how the system will behave under velocity step. And one can correlate, like if a person is, so it's a ferry, and suppose if you have just a support and you jump, what happens if it's a steep, if it's a very stiff board, then the force will be very high, and you may hurt your ankles. But if it's too soft, then it may bend and touch the water. So what you can see that there is contradictory requirement, and one has to get get the C, so that the value of C such that doesn't the displacement is not very high, but at the same time, the force should also not be very high. So you have to do a balancing act. Similarly, one can also give acceleration step input, and therefore the ft will be c times half at square, and this will be the displacement plot. So if that is the case, the acceleration will be given by a times 1 minus cos h omega t. This is the acceleration response, and these are the amplitude for displacement, velocity, and acceleration. And here also you will see the positioning error and the acceleration amplitude. So again, displacement and velocity, and these are the acceleration. So in mechanisms, we also talk about jerk because if you have the derivative of the acceleration, we get the jerk, and if we have the values, if the jerk is not 0, the third derivative, then it also give rise to a lot of issues. So what happens if it's a jerk step here, third derivative? So again, this is the response for jerk if there is a sudden jerk in the system, and this is the displacement, velocity, acceleration, and jerk. So, and in this case also you have a dynamic positioning error, and so in all these cases you see that there are positioning error associated, and it can be summarized here for different kind of step response. So the step in position, velocity, acceleration, and jerk, and what is the maximum error in positioning, velocity, acceleration, and jerk? It's not 0. It means one has to be aware of what kind of input is given and how. So whenever there is a step input, whether it's a position, velocity, acceleration, or jerk, so when you design the cams, what we realize that at various stages there will be a step input, and sometimes it's nearly impossible to avoid also. So we have to be aware, okay, what are the positioning error, the dynamic positioning error, and whether we need to introduce what kind of damping and how long it takes. So it's very important to know that and be aware of that and how to control that. That's definitely a challenge, and one has to know that. So the dynamics with respect to vibration, the system we are working with is case to case. We have many challenges, and these are something is open, and we have to keep working, and depending on the application, depending on the requirement, it can be very involved. Sometimes it can be very easy to solve also. So one has to be aware of, and we cannot neglect the dynamic issues altogether, but we have to be aware, and we have to always check whether it's possible to take care of that and what are the different methods. And definitely for that region we need different kind of feedback, the sensors, the actuators, how fast they are, how responsive they are. So not only our mechanical system but at the same time the control electronics. So that's why the precision is a mechatronics approach. If we really want to achieve a very high degree of precision and want to go or achieve the micron level of accuracy or even sub-micron level of accuracy. And many times in the semiconductor industry or in high-end equipments, we may want to go for nanometer kind of resolutions and accuracies. There is a very important to understand that how this dynamics plays a role and how fast, how slow we can do. In some places it's okay to go slow, but in many application going slow means we compromise with the yield, and therefore it's a very important to understand that what is the reasonable accuracy one can achieve, with the precision one can achieve with the reasonable speed. And of course there is always some kind of conflicting requirements, and we have to address that. So there are many cases, and all cases are different from each other. Whatever we covered is just just to give some idea that okay, these things we have to take care. And yes, we want to learn more, we can refer to these references. So very good book. So and it's mainly from Netherlands, and most of the work from Philips, and now ASML there. So and it's in English. The Dutch version is also there by Professor Koster, and Professor Summers, he has written the international edition, and in English, so translated into English. So very good book, and it's getting further translated by different researchers and authors. So one can look at it. At the same time, there are also very good books one can refer to whenever one venture into designing these kind of systems. So we'll continue with some cases and some topics, whatever left. We are almost at the end of the course, and but it's just the beginning, and we can explore together. Anybody having any issues and want to design systems for this kind of application, we can always discuss and work towards achieving the precision level required for different applications. Thank you.